So now that we have resolved the Gibbs paradox, let us see how we can correlate the thermodynamic quantities, other thermodynamic quantities like Gibbs free energy, Helmholtz free energy, chemical potential with the partition function. So let's talk first about the Helmholtz free energy. As you recall that since we had a problem with the definition of thermodynamic probability, so even though we got some expression for thermodynamic quantities, they might suffer the inaccuracy due to W, and therefore you need to find out the corrected expression of the thermodynamic quantity in terms of the partition function. That's our final goal, that if we know the partition function, so we then calculate. So partition function is a microscopic quantity, and our goal is to correlate that microscopic quantity with the macroscopic properties what classical thermodynamics define. So Helmholtz free energy A is one such quantity, and our goal would be now to see A as a function of Q, partition function. So as we know from thermodynamics, A is equal to E minus ds. This is the formula from thermodynamics. So we got S from our statistical thermodynamics, which we can put up here. So T and S we got as Nk ln Q by N plus E by T plus Nk. This is the expression of entropy what we got. So if we simplify, so this E minus Nkt ln Q by N, and then we have a minus E plus we have minus Nk. So therefore we get A is equal to minus Nkt ln Q by N minus Nk, minus Nkt, minus Nkt. There is a T here. So minus Nkt. This is the expression for Helmholtz free energy, and if you want to get the Helmholtz free energy for the monoatomic gas, you can simply write A is equal to minus Nkt ln 2 pi Mkt H square 3 by 2 V by N minus Nkt. So this is the expression of A for a special case of monoatomic gas. Okay, so this is the expression for Helmholtz free energy. What is the expression for chemical potential? Chemical potential, as you have seen in your classical thermodynamics part, perhaps the most important thermodynamic quantity. And how is it related to Helmholtz free energy or the Gibbs free energy? So mu can be written in terms of Helmholtz free energy del A del N at constant volume and temperature, whereas if you want to express in terms of Gibbs free energy, which is G, there you keep your pressure and temperature constant. Now since we already have A, we already have the expression of A, we can get chemical potential using that expression of A. which we got minus nkt ln q by n minus nkt. This is the expression of Helmholtz free energy we got. So now we have to do this derivative. So if you do the derivative of this, you should get finally minus kt. You can get out kt from both terms, and then you do del n of ln n ln q n ln q minus n ln n, and here we have plus n because we have taken the minus kt out, so we have plus n. Okay, so what is the result of this? Minus kt. So del n ln q is nothing but ln q. Here you have minus n, and ln n is 1 by n. We have another term from here, which is minus ln n plus 1. So we have minus kt ln q minus n by n minus ln n plus 1. So this two terms goes off, so we get minus kt ln q by n. This is my chemical potential. So chemical potential mu is minus kt ln q by n. This is a very important expression where we correlate a very important thermodynamic quantity, chemical potential mu, with a very important statistical thermodynamic quantity q, the partition function. So another very important thermodynamic quantity is the Gibbs free energy. So G. How is G related to the partition function? Now you know G, the Gibbs free energy, is related to the Helmholtz free energy H by this expression G is equal to H minus Ts. Now let's simplify it further. You can reach to the expression of G in terms of partition function in different ways. This is just one of the ways I'm trying to put up, but you can look at it in different you can look at it from different directions also. Since you already have H known, you already have S known from in terms of partition function. So you can straight away put H and S here, but I'm just trying to simplify it a little further. So H is nothing but E plus PV, and then I am putting Ts. I am writing E minus Ts plus PV. E minus Ts is nothing but Helmholtz free energy, and PV is nothing but nkt. PV is equal to nkt, and since I had the expression of A already ready, so I can just put expression of A which we had before. I suppose we had A is equal to minus, we had A is equal to minus nkt ln q by n minus nkt. So this expression I am putting there. So I am putting A is equal to minus nkt ln q by n minus nkt, and I have nkt kT here. So these two terms goes off. So what I get is G is equal to minus nkt ln q by n. This is the expression of Gibbs free energy in terms of the partition function q. Now in the previous slide you saw the expression for mu. So mu you got is equal to minus kT ln q by n, and here you got G is equal to minus nkt ln q by n. So therefore if you put back the expression of mu here, so you get G is equal to n mu. And this is again the expression what you get from classical thermodynamics. So this is the classical thermodynamic formula, what you can also derive from statistical thermodynamics formulation. So basically what we have seen so far is that if you have the understanding of quantum states, quantum energy levels, quantum definition of degeneracy, then you can come up with different expressions which relate various thermodynamic quantities like free energy, chemical potential, entropy, with the most important statistical thermodynamic quantity Q, the partition function. So since partition function basically tells how the particles are distributed over the different energy states and energy levels, if you know how the particles are distributed, which is the macroscopic information, so from there we can always get to know the thermodynamic quantities like G, H, S from Q, and that's what we have derived so far. So what is the way forward now from going from the quantum system to the biological system, or molecular system, where our system is much more complex than the small quantum system that we'll see now.